Hello, Internet. Today I'm here to talk about generative art, a universe of infinite and unpredictable possibilities. Generative art is a dynamic and continuously evolving field where creativity and technology intersect. Unlike traditional art, which depends entirely on the artist's direct input and vision, generative art utilizes systems, such as rules, algorithms, and autonomous processes, to bring creations to life. Welcome to the TouchDesigner 101 series. Today we'll discuss an innovative art form deeply connected to the techniques and processes commonly used in TouchDesigner to create art. In this video, we'll explore how generative art works, its historical roots, and some practical examples in TouchDesigner. Let's dive into the main topics of this video. 1. Understanding generative art. 2. Generative art. Before computers, historical systems of creativity. 3. TouchDesigner's role in generative art. Recreating iconic generative artworks. 5. Generative art and contemporary practice. Before we begin, I'd like to ask for a big favor. As you know, this channel has grown from 100 subscribers, and we're now approaching 10,000. This growth benefits everyone. More subscribers mean more opportunities for me to create better tutorials and content, and for you, it means access to even more in-depth knowledge about TouchDesigner. To keep this momentum going, remember that subscribing to the channel helps us all continue improving and bringing even more valuable content. Thank you for your support. Chapter 1. Understanding generative art. Let's break generative art into 3 key elements to better understand its essence. 1. The core idea, creativity through rules. At its foundation, generative art is about designing a framework, a set of rules, parameters, or instructions that governs the creative process. These rules act as the boundaries of play, setting the stage for how the artwork can evolve. While the framework provides structure and control, it also leaves room for infinite variation and spontaneity within those boundaries, making each iteration unique. Let's explore the most common families of parameters to modulate when designing rules for generative art. Color rules. A system might dictate that colors transition smoothly within a gradient, but the exact combinations and timing are determined dynamically. Shape parameters. Shapes might be restricted to specific geometric forms, such as triangles or circles, but their placement, size, and rotation vary unpredictably. Behavioral guidelines. Elements could follow basic rules of interaction, such as particles gravitating toward a center or avoiding overlaps, producing organic, lifelike movements. This method achieves a perfect equilibrium between structure and spontaneity. Retro moment. Frieder-Naki. In the 1960s, Frieder-Naki pioneered the use of algorithms to create art, producing intricate drawings using early computers. His work demonstrated the potential of generative systems to redefine artistic practice, blending human creativity with the precision of machine execution. 2. The power of algorithms. Algorithms, the sequential instructions executed by a computer, serve as the core engine of generative art. By encoding creative rules into algorithms, artists can design dynamic systems that generate endless variations. Let's explore 3 of the most common algorithms used in generative art. Noise functions, such as Perlin noise, produce smooth, pseudo-random patterns, perfect for mimicking natural elements like clouds, water, or terrain. Fractals are generated through recursive algorithms, creating endlessly complex, self-repeating patterns. These range from geometric designs to natural forms like ferns or coastlines, showcasing intricate beauty from simple rules. Cellular automata simulate evolving patterns based on simple grid rules. Each cell changes state depending on its neighbors, creating emergent behaviors, like Conway's game of life. Used in generative art, they mimic natural growth and movement, producing dynamic textures and evolving animations. This series of algorithms was developed to advance computer graphics, although some, like fractals, originated from abstract mathematical studies, such as Mandelbrot's geometry, without an initial intent for artistic or simulation purposes. Their creative use emerged later, as artists and scientists recognized their potential to model both natural and abstract forms. Generative artists found ways to repurpose these algorithms to craft unpredictable results and redefine artistic expression, fueling a new form of art now showcased in museums dedicated to the intersection of art and technology. Retro moment. Vera Molnar, often regarded as the mother of generative art, revolutionized the field in the 1960s and 1970s by using computers to explore geometric abstraction. Through early programming languages, she introduced randomness into her compositions, challenging traditional notions of authorship and creating works that balanced control with unpredictability. Decades later, pioneers like Casey Reese and Ben Fry expanded these possibilities by developing frameworks such as processing, enabling a new wave of algorithmic art and empowering a generation of artists to explore the new limits of creativity. The final part of understanding generative art lies in the following question: where does the role of the artist end, and where does the machine's begin? Historically, the artist has been seen as the creator, shaping every detail of their work. In generative art, this traditional paradigm shifts as the artist relinquishes some control to a system, an algorithm, a program, or even artificial intelligence that carries out parts of the creative process autonomously. This collaboration between human intention and machine execution challenges established notions of authorship and creativity. This raises the question: does the machine truly create or simply follow instructions? While autonomous, its outputs are bounded by human intention, creating a sense of co-authorship where neither fully owns the final work. Generative art embodies contemporary creative trends by recognizing the machine as a collaborator rather than merely a tool. It resonates with movements that challenge the notion of the genius artist, embracing technology's transformative role in art. Here, the artist becomes a system architect and partner, while the machine takes on an active role in shaping outcomes, blurring boundaries, and redefining the nature of creativity in our interconnected digital era. Chapter 2. Generative Art. Before computers, historical systems of creativity. Generative art, as a concept, predates computers and even the Industrial Revolution. Artists and composers have long used systems, rules, and processes to create works that involve an element of unpredictability or systematic generation. These historical examples highlight how the idea of defining parameters to produce art has been a recurring theme across centuries. Let's take a look at some of the most well-known examples. 1. Wolfgang Amadeus Mozart's dice music. Mozart created a musical game known as musical dice game in the late 18th century. It was a system where players used dice rolls to assemble pre-composed measures of music into a complete composition. Each roll corresponded to a specific measure from a predefined table, resulting in a unique piece every time the game was played. Why it qualifies as generative art? Mozart's system embodies the principles of generative art by using predefined rules, the table of measures, and randomness, the dice rolls, to produce an infinite variety of musical compositions. While the composer set the framework, the outcome depended on chance, introducing unpredictability into the creative process. 2. Islamic geometric patterns. In Islamic art, particularly in architecture, artists used mathematical rules and geometric principles to create intricate repeating patterns. These designs often followed strict guidelines for symmetry, proportion, and repetition, yet they allowed for infinite variation within those constraints. The designs were both highly systematic and aesthetically captivating, demonstrating a deep understanding of geometry and abstraction. Why it qualifies as generative art? The artists set a framework of rules for constructing patterns, much like a modern generative system. Although constrained by the principles of geometry, the interplay of shapes, lines, and repetition created an emergent complexity, producing unique results within a predefined structure. Retro moment. Harold Cohen developed AARON, a groundbreaking program capable of generating autonomous artworks. Aaron blurred the line between artist and machine, raising philosophical questions about creativity and redefining the role of algorithms in artistic expression. 3. The I Ching and aleatoric art. The I Ching, an ancient Chinese text, has been used for thousands of years as a method for generating philosophical insights and guiding decision-making. In the 20th century, artists like John Cage used the I Ching to introduce randomness into their compositions. Cage would toss coins or consult the text to determine musical elements like pitch, duration, and dynamics in works such as Music of Changes. Why it qualifies as generative art? The I Ching provided a system of rules and chance operations to guide the creative process, making Cage a facilitator rather than a direct creator. His use of randomness aligned with generative principles by blending control, the framework of the I Ching, with unpredictability, the random results of coin tosses. These examples show that the concept of generative art has existed long before modern technology. In each case, artists used systems of rules, randomness, and structured frameworks to create works that balanced order and unpredictability. Chapter 3. TouchDesigner role in generative art. TouchDesigner, with its node-based architecture and real-time capabilities, serves as an ideal environment for generative artists to explore. allowing us to create complex systems through a visual interface, making it accessible to those with or without deep programming knowledge. TouchDesigner, along with programs like processing and open frameworks, occupies a critical position in the evolution of generative art, not merely as a tool, but as a medium that redefines the ontology of artistic practice in the digital age. These environments offer artists an unparalleled capacity to design systems of interaction and emergence, foregrounding the process over the object and shifting the locus of creativity from the individual artist to a dialogical interplay between human intention and algorithmic execution. Beyond democratizing computational aesthetics, TouchDesigner fosters the co-evolution of art and technology. Its real-time approach, procedural design, and cross-modal integrations expand creative possibilities while challenging traditional notions of authorship, agency, and temporality in art. In many ways, these programs transform artists from creators to curators of systems, embodying postmodern concepts of decentralization and unpredictability. This aligns with contemporary media theory, which prioritizes process and interaction over static artifacts. Chapter 4: Recreating Generative Artworks. We're going to create 3 examples to honor some of the main influences of generative art. I know there are many more relevant figures, but we don't have enough time to cover them all. So, let's dive into the first one. This is the project we are going to review, where I will simulate and reinterpret some of my favorite artists, from whom I have taken many concepts to create my compositions. So, let's get started. This is a reinterpretation of the work by Casey Reese. He is one of the creators of processing, as I've already mentioned, and my interpretation is that he was used a type of noise with fields. So, I created a composition using noise that simulates this kind of fields. However, since this is a reinterpretation, I've obviously done something a bit different, but it is heavily influenced by the main concept. Next, we'll explore Molnar's work, which we also discussed previously. Essentially, her system, based on incredibly simple rules, generates fascinating patterns and is one of the easiest networks to recreate. Finally, we will examine another work by Frieder Nake. In this project, the rules are somewhat implicit, and I have applied some instances to generate a this work, let's say with a different dynamic. Nevertheless, the rules that create this graphic universe remain somewhat similar. We have a line that rotates and moves across different axes. This line follows a figure, and in this case, I use that concept as inspiration to recreate and reinterpret these compositions. You can find this project on my Patreon, where it will be available in its entirety. Just a heads up, we'll look at Nake's networks, and then Vera Molnar's, which is very straightforward. However, the final network, if you want to replicate it exactly, is slightly more complex. I don't want to make this video overly long, so this project will be available as a project file on my Patreon, but I will provide a quick overview of how it was built. All right, let's begin with the artist, Frieder Nake. We'll use instances, so the first step is to create the primary operators for this network. We start with a box, followed by a transform. After that, we add a material. Perfect. Now, we right-click and create a geo operator. Basically, we'll use a classic network to manage 3D environments. We create a camera and an ambient light. We position these at the top. Perfect. Now, we need to create the texture network, that is, the top operators. We start with a render top. If I hold down the Shift key, I can keep adding operators. Along the way, I add a feedback, followed by a level operator. Then, we add an add top. Perfect. I organize everything and finally reference the feedback. To finalize this network, we create an RGB key and finally an out operator. We select all the tops, go to Common tab, and select parent panel size. Personally, I like working in a vertical resolution, so if you prefer, you can copy these values. To preview the screen, divide the workspace by selecting Top View. Activate the out operator, right-click, and disable the Display Background Tops option. Now, the next step is to create specific parameters in the transform operator to make it rotate. Additionally, I need to create a grid, which I'll use for the object instances. Finally, we build 2 additional networks we'll use here. First, we create a pattern operator and connect it to a null, which we'll name scale. Then, we duplicate this pattern and name the duplicate one to rotation. Perfect. At this point, we have nearly all the elements for the network. We just need to create the operator that generates the animations. We create an LFO, connect it to a math, and finally, to a null, which we call also scale. We duplicate this setup, and the duplicate is called pivot point. Nice. Let's review all the parameters. Don't forget to select the render top and use the same resolution throughout the project. We manipulate the grid to create the instances. Before that, I recommend lowering the opacity in the level operator to 0 so we can see exactly what we're doing without the feedback interfering. We adjust the grid to make it more vertical. For rows and columns, we use low values like 5 by 5. Then, we select the geo operator, enable the instances, and reference the grid to the translate parameters. We only use the X and Y axes. Now we have a grid where all the lines are repeating. Now let's work on the patterns. I don't want this to be too symmetrical, so I go to the first pattern named Scale, select Channel, and to create 3 channels carrying the same signal, I write the following: Scale, open brackets, X, Y, Z, and close brackets. This creates 3 distinct channels. I do the same for the rotation pattern, naming it rotation. Since rotation is measured in degrees, I'll also need a math operator here. Next, I check the number of points. If I click the middle mouse button, I see we have 25 points on this grid. I need the pattern to have the exact same number of points. I select both patterns and set their count to 25. Now, I can reference scale into the scale operator and select all 3 axes. This creates a deformation. For rotation, I do the same, referencing rotation and selecting all 3 axes. At this point, nothing significant should happen. In the math operator, I set a multiplier of 180. This works well, but we could also try 360 to see different results, though I'll leave it at 180. We select both patterns in the chop and apply a random function to make them less uniform. For the rotation pattern, I adjust the offset with the classic abs_time.seconds script animation. Now we have a rotation. Finally, we can increase the amplitude and scale for a more noticeable effect. I test various values until I find one that works. I want more spacing between the clones, so I increase the values significantly in the grid, for example, 10 by 30. We adjust the camera to frame everything properly. At this point, the scaled values look great, and all that's left is to create a movement. For the first LFO named Scale, I set the frequency to 0.25 and leave the other settings as they are. I select Gaussian as the type. In the math operator, I map the range from -1 to 1 and 2 to 30. This creates a slightly exaggerated scale. In the transform, I reference the LFO on only to the x-axis. Now we have an aleatory movement in the scale. For the second LFO, I set a frequency of 0.1 and an amplitude of 0.1. I temporarily disable the math operator and reference this to the pivot point on all 3 axes. Now, the pivot point creates a more interesting rotational flow. Finally, I raise the opacity in the level operator to see the result. Perfect. This network is quite simple, but it allows for a lot of experimentation with the parameters to achieve different results. The next network, inspired by Vera Molnar, is even simpler. We'll exclusively use top operators. We start with a rectangle, followed by a feedback, a transform, and finally, an add top. We position these nodes here, connect the last operator to the feedback, and clone all this network. Perfect. Next we create a layout operator, a crop, a tile operator, RGB key, and finally, and out top. Everything is now in the network. Connect the other feedback network to the layout. We replace the rectangle with a select operator, referencing the rectangle above, and then replace these connections. This is necessary because we need the exact same parameters for both rectangles, so it's better to use just one. Adjusting the parameters, we make the rectangle smaller, let's say a size of 0.8. I remove the fill color and set the border color to white. The border thickness can be adjusted to your preference. Perfect. In the transform operator of the first feedback, I apply a rotation animation using abstime.seconds. For the scale, I use a value of 0.8 on both axes. For the second feedback, I want rotation without movement, so I apply similar settings but ensure the scale is also at 0.8. Remember to upscale the resolution of the rectangles so they don't look too pixelated. Finally, I select the layout operator and configure it to top-bottom. In the crop operator, I remove the excess alpha channel using values like 0.25 and 0.75. At this point, we have something that resembles Vera Molnar's work. If you want it to be subtler, you can adjust the values. This network is extremely straightforward but very powerful, as it allows you to create many variations using basic operations. The last example is inspired by Casey Reese. I'll briefly explain what I did, although we won't recreate it from scratch to keep this video concise. This project will also be available on Patreon. For this setup, I used a box operator, combined with a material operator and a ramp top. The ramp was animated with the phase parameter to create movement. I also instanced this box using a grid operator in chops. To make it more dynamic, I combined the X and Y coordinates with a Z value derived from a noise chop. By converting these noise values into chops, I could integrate them with the X and Y coordinates, allowing the instances to reflect the noise-generated movement. In post-processing, I added a feedback and a displaced top to give it a more metallic effect. One of my go-to tricks is using a composite operator with a negate blending mode. You can experiment with other blending modes to achieve unique and interesting results. Finally, I adjusted the colors in the post-processing phase to fine-tune the overall aesthetic. This network builds on concepts explained in other tutorials on my channel. I encourage you to experiment with the size of elements or even add a transform operator to explore different dynamics. For example, making objects larger or smaller can completely change the feel of the generated forms. It's highly customizable. Everything in this project is neatly organized within the project file, which you'll find on my Patreon. I encourage you to play around with the parameters and discover your own variations. With this, we transition into the final section, focused on generative art. Chapter 5, Generative Art in Contemporary Practice. Generative art has evolved into a prominent field at the intersection of art and technology, reflecting how algorithms, data, and systems redefine creativity in the digital age. Moving beyond its early experimental roots, generative art now encompasses diverse practices, from visual abstraction to immersive installations. This practice aligns deeply with contemporary art's move toward interactivity, decentralization, and the blurring of boundaries between the creator, the audience, and the medium itself. Core characteristics of generative art in the contemporary era. Interactivity. Modern generative art often includes audience participation, where the viewer's actions or environmental data directly influence the artwork's evolution. Real-time systems. Many works operate in real time, leveraging platforms like TouchDesigner, processing, or AI frameworks to create fluid, evolving pieces. Cross-disciplinary integration. Generative art incorporates principles from fields like biology, physics, and artificial intelligence to create works that are both aesthetic and conceptually rich. Key artists and their contributions. Of course, there are hundreds of artists who represent this movement, but I will have to limit myself to a few examples that I consider particularly interesting to explore. At the end of the video, I'll share a list of 20 artists you can explore who are deeply involved in generative art. Mario Klingemann, a pioneer of AI-generated art, explores themes of human creativity and machine autonomy. His works, such as Memories of Passers-by Warn, use neural networks to produce continuously evolving portraits. By repurposing AI algorithms, Klingemann questions the relationship between the artist and the machine, challenging traditional authorship. Casey Reese has empowered countless artists to delve into generative practices. His own works often visualize complex data systems or reinterpret classical forms through algorithmic lenses. Rees's installations and prints demonstrate how generative systems can produce aesthetic complexity while maintaining conceptual depth. Michael Hansmeyer combines generative design with architecture creating intricate structures that blend natural forms with algorithmic precision. His digital grotesque project involves computational processes to generate ornate, immersive architectural spaces. These works exemplify how generative methods can extend beyond the digital screen into physical, tangible creations. Broader implications. Contemporary generative art is not just about aesthetic innovation. It also addresses deeper cultural and philosophical questions. Works often engage with issues like the role of technology in society, ecological interconnectivity, and the ethics of machine creativity. By leveraging the unpredictability of systems, generative artists encourage viewers to embrace complexity, randomness, and emergent beauty. This practice, rooted in mathematical principles yet deeply human in its intent, continues to redefine the boundaries of what art can be in an increasingly interconnected and data-driven world. It is a dynamic field, constantly pushing the limits of technology and creativity while challenging our understanding of art, authorship, and audience participation.